Abstract, organizations have moved beyond questioning whether artificial intelligence delivers value. The critical challenge has shifted to organizational integration, restructuring work, redefining roles, and redesigning processes to capture demonstrated AI value while managing risks inherent in sociotechnical transformation. This article examines the AI integration gap, the distance between technical capability and organizational value realization, and synthesizes evidence on effective change leadership practices. Drawing on organizational change theory, technology adoption research, and emerging practitioner accounts, it identifies patterns in how leading organizations navigate structural ambiguity when established implementation models do not exist. The analysis reveals that successful AI integration requires simultaneous attention to work redesign, capability development, governance frameworks, and psychological contracts, with experimentation emerging as the dominant change methodology in the absence of proven blueprints. The executive conversation around artificial intelligence has fundamentally shifted. In boardrooms and leadership teams across industries, the question is no longer whether AI can deliver organizational value. Mounting evidence confirms it can. Instead, leaders increasingly grapple with a more complex challenge: how to restructure work, roles, and processes to actually capture that value within existing organizational systems. This shift reflects a maturation in organizational AI understanding, but also exposes a critical gap. AI development labs have focused predominantly on technical capability, building systems that can just do work with increasing autonomy and sophistication. Software engineering provides a clear example. AI assisted coding appears to accelerate development workflows, yet organizations struggle to answer fundamental questions about how to reorganize engineering departments, which roles require redefinition, and what processes should govern AI augmented development cycles. The integration challenge is particularly acute because organizations face structural ambiguity without established models to emulate. Unlike previous technology waves, where leaders could benchmark against early adopters and follow proven implementation patterns, AI's breadth and recency mean even the most advanced organizations are experimenting in real time. As Davenport and Ronenke, 2018, observe in their analysis of over 250 AI projects, companies attempting to scale AI beyond pilot projects consistently encounter organizational barriers that dwarf technical obstacles, with integration challenges around workflow redesign, skill gaps, and change management proving far more limiting than algorithm performance. This article addresses the AI integration gap from an organizational change perspective, synthesizing evidence on how leading organizations are restructuring work and managing transformation when proven blueprints do not exist. The AI integration landscape, defining the integration gap in organizational context. The AI integration gap describes the distance between demonstrated technical capability and realized organizational value. Unlike traditional technology adoption curves that primarily address user acceptance and technical deployment, AI integration encompasses deeper structural questions: how work gets decomposed, how authority and decision rights get allocated, how performance gets measured, and how organizational boundaries between human and machine contributions get negotiated. This gap manifests most visibly in the disconnect between AI system capabilities and organizational readiness to absorb those capabilities. Fountain et al. 2019 identified this pattern across multiple industries in their Harvard Business Review analysis, finding that technical AI maturity frequently outpaced organizational change capacity, with companies achieving successful pilot deployments, yet struggling to translate those successes into scaled, sustained value creation. The gap widens when organizations approach AI through a technology lens rather than recognizing it as requiring fundamental work redesign. Software engineering illustrates the integration challenge with particular clarity. While AI coding assistants show promise in accelerating specific development tasks, these potential productivity gains don't automatically translate into organizational outcomes. Engineering leaders must address cascading questions. If individual developers complete tasks faster, how should team composition change? What new quality assurance processes prevent AI-induced defects? How should performance management evolve when productivity benchmarks shift? What skills require new investment? These questions lack standardized answers because the organizational structures that might provide them are themselves in flux. State of practice, experimentation as default methodology. Current organizational practice reflects widespread recognition that established implementation models do not exist for comprehensive AI integration. Rather than following proven blueprints, leading organizations have adopted experimentation as their primary change methodology, a necessity born from structural ambiguity rather than a choice among alternatives. This experimentation dominant approach appears across industries and organizational contexts. Organizations pilot AI applications in specific domains, discover unanticipated workflow implications, redesign roles accordingly, then apply those learnings to adjacent processes. The pattern suggests a fundamental shift from traditional change management, where organizations plan comprehensively, then execute, toward continuous adaptation, where learning emerges through implementation. The absence of established models creates both risk and opportunity. Organizations lack proven templates to de-risk transformation initiatives, increasing the probability of costly missteps and organizational resistance. Simultaneously, this ambiguity means competitive advantage accrues to organizations developing effective integration approaches rather than simply deploying superior technology. Research tracking AI adoption across organizations suggests that those successfully scaling AI share characteristics of active experimentation culture, cross functional governance structures, and explicit investment in organizational change capabilities rather than exclusively technical infrastructure. Notably, even AI development organizations demonstrate limited conception of how organizational integration occurs. Laboratory environments optimize for technical performance, accuracy, speed, capability breadth, with integration treated as an external implementation concern. This orientation produces AI systems designed to do work autonomously without corresponding frameworks for organizational absorption. The resulting mismatch places integration burden entirely on adopting organizations, many of which lack specialized organizational change expertise and struggle to translate technical capabilities into operational reality. Organizational and individual consequences of integration gaps. Organizational performance impacts. Organizations failing to bridge the AI integration gap experience measurable performance consequences despite technology investments. The most direct impact manifests as unrealized productivity gains. AI capabilities exist within organizational boundaries, but fail to translate into operational improvements because surrounding work structures remain unchanged. Brynjolfsson et al. 2017 documented this pattern empirically in their analysis of information technology and productivity, finding significant lag between technology investment and productivity realization, often measured in years rather than months, with the lag primarily attributable to organizational factors rather than technical limitations. Their research revealed that productivity gains require complementary investments in process redesign, skills development, and organizational structure changes, with many organizations underinvesting in these intangible assets relative to technology spending. The integration gap also generates competitive vulnerability. When organizations in the same industry pursue AI capabilities simultaneously, those developing effective integration approaches capture disproportionate advantages. An organization with moderately sophisticated AI technology, but strong integration capabilities, will typically outperform competitors with superior technology, but weak integration. Quality and risk implications deserve particular attention. Poorly integrated AI systems introduce new failure modes. Automated decisions without appropriate human oversight, algorithmic outputs that violate organizational policies or regulatory requirements, or AI generated work products that lack quality controls. Organizations deploying AI assistants without corresponding process adaptations may encounter increased defect rates, security vulnerabilities, and technical debt accumulation as workers accept AI suggestions without fully understanding implications. Individual and stakeholder impacts. Integration gaps create significant consequences for employees navigating AI transformed work environments. Role ambiguity emerges as a primary stressor. When AI capabilities arrive without clear delineation of human versus machine responsibilities, employees experience uncertainty about their value contribution, appropriate skill investment, and career trajectory. Organizational psychology research indicates role ambiguity strongly correlates with job dissatisfaction, reduced organizational commitment, and increased turnover and tension. Bowling et al., 2017. In AI integration contexts, this ambiguity intensifies because employees simultaneously encounter new technology, shifting performance expectations, and unclear future role definitions. Software engineers, for example, face uncertainty about whether to invest in traditional coding skills when AI assistance handles routine implementation, what new skills will prove valuable, and how their professional identity should evolve. The integration gap also generates skill mismatches that leave employees feeling unprepared for AI augmented work. Organizations deploying AI without corresponding training and capability building create environments where employees lack competence to effectively leverage new tools, collaborate with AI systems, or understand system limitations. This skill capability gap produces stress, reduces self efficacy, and can trigger resistance to AI adoption as employees protect themselves from exposure to tasks they feel unqualified to perform. Equity implications warrant attention as integration gaps often distribute AI benefits and costs unevenly. In organizations lacking intentional integration design, AI access and productivity gains tend to concentrate among employees already possessing technical sophistication or positional power, while employees in routine roles may experience AI primarily as surveillance, displacement threat, or work intensification without corresponding empowerment. Kellogg et al. 2020 documented this pattern across multiple organizational contexts, where algorithmic management systems enabled intensified monitoring and performance pressure without providing workers with meaningful decision authority or capability enhancement. Evidence based organizational responses, transparent communication, and psychological contract renegotiation. Effective AI integration begins with explicit communication about organizational change scope and implications for work and roles. Research on technology driven organizational change consistently demonstrates that transparency regarding change rationale, expected impacts, and implementation timelines reduces employee resistance and anxiety while building change commitment. Bordia et al., 2004. In AI integration contexts, transparent communication addresses the role ambiguity and displacement anxiety that integration gaps create. Organizations successfully navigating AI integration proactively communicate that AI capabilities will reshape work rather than simply augment existing processes, explicitly name roles and functions likely to experience significant change, and outline organizational support mechanisms for skill development and transition. Effective transparency approaches include multi channel communication campaigns that reach employees through diverse media, town halls, direct manager conversations, written documentation, interactive workshops, rather than single announcement approaches. Specificity about AI capabilities and limitations to establish realistic expectations and prevent both over reliance and unnecessary fear. Honest acknowledgement of uncertainty about ultimate organizational structure when that uncertainty genuinely exists, rather than premature commitment to specific models. Regular updates as integration progresses to demonstrate leadership attention and provide opportunities for employee input. Clear articulation of decision principles guiding integration choices, even when specific decisions remain pending. Psychological contract renegotiation represents a deeper dimension of communication strategy. AI integration inherently disrupts implicit understandings between employees and organizations about job security, skill requirements, performance expectations, and career paths. Rousseau, 1995, defines psychological contracts as individual beliefs about reciprocal obligations between employees and employers, with contract violations producing reduced commitment and increased turnover. Organizations successfully renegotiating psychological contracts for AI integration make explicit the new reciprocal obligations. Employees commit to continuous learning, experimentation with new work methods, and collaboration with AI systems. Organizations commit to investment in capability development transition support, and recognition systems aligned with AI augmented performance. Making these new mutual obligations explicit through formal communication, policy changes, and leadership modeling helps prevent the psychological contract violation that occurs when employees perceive AI integration as unilateral imposition. Structured experimentation and learning systems. Given the absence of established integration models, leading organizations institutionalize experimentation as a formal change methodology rather than treating it as ad hoc exploration. This involves creating organizational structures, governance mechanisms, and resource allocation processes that enable rapid iteration while capturing learning for broader application. Effective experimentation systems share several characteristics supported by organizational learning research. They establish clear learning objectives beyond immediate performance outcomes, create safe environments for failure without career penalty, implement structured documentation of insights, and build feedback mechanisms that disseminate learnings across organizational boundaries. Edmondson, 2011. Structured experimentation approaches include cross functional integration teams with explicit authority to redesign work processes, combining domain expertise, technical AI knowledge, and organizational change capability. Time boxed pilots with defined learning questions rather than open ended exploration, focusing experimentation on specific integration challenges. Rapid iteration cycles, typically measured in weeks rather than months, that enable quick learning and course correction before significant resource commitment. Formal retrospectives and documentation that capture not just whether pilots succeeded but why, identifying replicable patterns and context specific factors. Lighthouse project portfolios that span diverse organizational contexts, enabling pattern identification across different integration environments. Staged scaling gates requiring demonstrated integration capability before expanded deployment, rather than scaling based solely on technical performance. The learning system dimension extends beyond individual experiments to organizational knowledge capture. Organizations effectively managing AI integration develop mechanisms to synthesize insights across experiments, identify emerging patterns, and codify preliminary best practices while maintaining appropriate humility about their provisional nature. This often involves dedicated integration teams or centers of excellence that aggregate learning, provide consulting support to new initiatives, and maintain living documentation of integration approaches and their outcomes. Role redesign and skill development. Realizing AI value requires explicit redesign of roles and deliberate development of new capabilities, rather than assuming existing roles will naturally adapt. Research on work design demonstrates that technology capabilities don't automatically translate into effective work practices. Intentional design of tasks, responsibilities, and interactions determines whether technology potential becomes performance reality. Parker and Grote, 2022. Role redesign for AI integration addresses several dimensions: task allocation between humans and AI systems, new responsibilities for AI oversight and quality assurance, collaboration patterns in human AI teams, and decision rights regarding when to accept versus override AI recommendations. Organizations leaving these dimensions undefined create the role ambiguity previously discussed, while those proactively redesigning roles provide clarity that enables effective performance. Effective role redesign strategies include human centered task analysis that systematically evaluates which work components AI should handle, which require human judgment, and which benefit from human AI collaboration. New specialist roles such as AI quality auditors or human AI collaboration facilitators that emerge from integration needs. Elevated judgment responsibilities for roles where AI handles routine execution, redirecting human effort toward exception handling, contextual interpretation, and strategic decision making. Boundary spanning roles that translate between technical AI teams and operational business functions. Hybrid role definitions that combine traditional domain expertise with AI collaboration skills, rather than segregating AI roles from traditional roles. Skill development must parallel role redesign. Organizations successfully integrating AI invest systematically in both technical skills, understanding AI capabilities and limitations, effective interaction patterns, data interpretation, and adaptive skills. Judgment about when AI recommendations prove inappropriate, creative problem solving in novel situations, collaboration with AI systems. Critically, skill development extends beyond one time training to continuous learning systems that evolve as AI capabilities advance. Organizations implementing advanced automation technologies have found that restructuring production roles from direct task execution toward supervisory responsibilities, exception handling, and continuous improvement activities requires substantial training investments and organizational patience as workers develop new competencies. This pattern applies broadly across industries, as AI handles routine execution while humans take on elevated judgment and oversight roles. Governance frameworks and decision rights. AI integration without clear governance creates operational risk and undermines value capture. Effective governance establishes decision rights, accountability structures, escalation processes, and risk management mechanisms appropriate for human AI collaborative work. Governance challenges in AI integration differ from traditional technology governance because AI systems exhibit autonomy, opacity, and probabilistic rather than deterministic behavior. Decisions about when humans must review AI outputs, who bears accountability for AI influenced decisions, and how to handle edge cases require explicit frameworks rather than informal resolution. Governance framework elements include tiered autonomy levels defining which AI applications can operate independently, which require human in the loop review, and which serve purely advisory roles. Accountability mapping clarifying human accountability for AI influenced decisions across different risk levels and domains. Quality assurance processes for AI outputs, including sampling strategies, error detection mechanisms, and continuous performance monitoring. Escalation pathways enabling workers to override AI recommendations when contextual knowledge suggests alternatives. Cross functional governance bodies bringing together business, technology, risk, and legal stakeholders to address integration issues. Audit and compliance mechanisms appropriate for AI augmented processes, particularly in regulated industries. Healthcare organizations face particularly stringent governance requirements given patient safety implications and regulatory oversight. Leading health systems implementing clinical AI establish clear protocols defining which applications require physician review before implementation, how AI assisted decisions get documented in medical records, and how accountability flows when AI recommendations influence clinical outcomes. Effective governance in high stakes environments requires explicit attention to transparency, contestability, and human override capabilities, even as automation increases. Financial services organizations similarly require robust governance given regulatory compliance obligations. When banks deploy AI for credit decisions or fraud detection, governance must address not only operational effectiveness, but also fairness requirements, regulatory examination standards, and audit trails that enable review of AI influenced decisions. Process integration and workflow redesign. Technology value realization depends fundamentally on process integration. Organizations deploying AI as standalone tools without redesigning surrounding workflows typically achieve minimal value. Those redesigning end to end processes to leverage AI capabilities while addressing its limitations achieve substantial gains. Process integration addresses how information flows between human workers and AI systems, how work gets sequenced to optimize human AI collaboration, where decision points occur, and how exceptions get handled. This requires process analysis and redesign expertise rather than purely technical skills. Process integration strategies include value stream mapping of current state processes to identify integration opportunities and understand handoff points. Human AI workflow design that sequences tasks to leverage respective strengths, such as AI handling pattern recognition and data processing, while humans apply contextual judgment. Exception handling processes for situations where AI cannot generate reliable recommendations, preventing workflow bottlenecks. Feedback loops that enable human corrections or overrides to improve AI system performance over time. Integration with existing systems to ensure AI tools don't create isolated workflows requiring duplicate data entry or parallel processes. Manufacturing organizations implementing advanced automation have found that successful integration requires redesigning production workflows to enable effective human machine collaboration. Rather than simply replacing human workers with automated systems, effective approaches design processes where humans and automation contribute complementary capabilities. Automation handling repetitive precision tasks, while humans manage variability, quality judgment, and adaptive problem solving. Process integration proves particularly critical in customer facing applications, where poor human AI handoffs create service failures. Organizations successfully integrating AI into customer service redesign interaction flows to ensure seamless escalation when AI systems encounter requests beyond their capabilities, preserve context when transferring from automated to human agents, and enable human agents to override AI suggested responses when customer specific knowledge warrants different approaches. Building long term AI integration capability, continuous learning and adaptation culture. Sustainable AI integration requires embedding continuous learning into organizational culture rather than treating integration as a finite project. Given AI's rapid capability evolution, organizations must build adaptive capacity that enables ongoing work redesign as technologies advance and organizational understanding deepens. Learning culture for AI integration encompasses several dimensions. It involves normalizing experimentation and intelligent failure, creating mechanisms for capturing and disseminating insights, building reflective practice into work routines, and establishing psychological safety that enables employees to surface integration challenges without fear of blame. Organizations cultivating this culture implement regular retrospectives examining AI integration effectiveness, establish communities of practice where employees share AI collaboration approaches, and create forums for discussing AI limitations and failure cases. Leadership plays a critical role in modeling learning orientation, acknowledging uncertainty, celebrating experiments that generated insights despite unsuccessful outcomes, and visibly adjusting strategies based on new information. The continuous learning imperative intensifies as AI capabilities advance. Generative AI represents a qualitative capability shift from predictive AI, requiring organizations to revisit integration approaches developed for earlier AI generations. Organizations with strong learning cultures adapt more effectively to these capability shifts because they've built capacity for integration experimentation rather than treating specific integration solutions as permanent. Distributed leadership and empowered experimentation. Centralized integration approaches struggle with AI's breadth and context specificity. Effective long term integration capability requires distributed leadership that empowers employees across organizational levels to experiment with AI applications relevant to their work contexts. This involves shifting from command and control change management toward enabling frameworks that provide guardrails while encouraging local adaptation. Organizations establish principles, governance boundaries, and support resources, then empower teams to design AI integration approaches fitting their specific contexts. Distributed leadership mechanisms include grassroots innovation programs that fund employee initiated AI experiments addressing local work challenges, integration coaches or facilitators embedded in business units who provide expertise without controlling integration decisions, lightweight approval processes that enable rapid experimentation within defined risk parameters while maintaining governance for high risk applications, peer learning networks connecting employees across organizational boundaries who are addressing similar integration challenges, visible recognition for teams demonstrating effective integration, spreading best practices through social proof. Distributed leadership proves particularly valuable in large, complex organizations where local context knowledge exceeds central leadership's detailed understanding. Frontline employees often possess superior insight into which AI capabilities would prove valuable in their specific work contexts and which integration approaches might prove feasible given local constraints. Organizations tapping this distributed knowledge through empowered experimentation access richer integration possibilities than centralized planning could generate. As Nambison et al. 2017 discuss in their analysis of digital innovation, successful organizations create scaffolding that enables distributed experimentation while maintaining coherence, establishing platforms, standards, and governance frameworks that guide without constraining local adaptation. This balance between centralized infrastructure and distributed innovation proves critical for AI integration at scale. Strategic workforce planning and transition support. Long-term integration capability requires proactive workforce planning that anticipates skill evolution and provides meaningful transition support for employees whose roles undergo significant change. Organizations treating workforce implications as afterthoughts rather than strategic priorities generate resistance, lose institutional knowledge, and fail to build capabilities required for AI-augmented work. Strategic workforce planning for AI integration maps current workforce capabilities against projected future needs, identifies skill gaps requiring development, and designs transition pathways for roles experiencing substantial transformation. This planning occurs at organizational scale rather than individual transaction level, examining workforce architecture holistically. Transition support mechanisms address both practical and psychological dimensions of work transformation. Practical support includes structured reskilling programs, job rotation opportunities, enabling skill development, and potentially redeployment assistance for employees whose roles face elimination. Psychological support includes career counseling, transparent communication about role evolution, and recognition that identity reconstruction requires time when professional roles change fundamentally. Workforce planning and transition elements include skills mapping and gap analysis conducted regularly as AI capabilities evolve, reskilling pathways with clear learning objectives, time commitments, and advancement opportunities. Job architecture, redesign creating new role categories that combine domain expertise with AI collaboration capabilities. Transparent communication about roles facing significant change or potential elimination, with sufficient lead time for employees to prepare. Internal mobility programs that prioritize redeployment of affected employees to emerging roles. Transition support resources, including career counseling and skill assessment. Large organizations in technology-intensive industries have demonstrated that comprehensive workforce transformation programs can successfully help employees transition from legacy skill sets toward emerging capabilities. These programs demonstrate organizational commitment to workforce development as technology reshapes work, building employee trust that supports broader transformation initiatives. Healthcare organizations face particularly acute workforce planning challenges as clinical AI applications evolve. Successful health systems are redesigning clinical team structures to incorporate new roles that bridge between care delivery and AI systems, coordinate AI assisted care pathways, and manage population health using algorithmic insights. These role innovations require deliberate workforce planning rather than organic emergence. Conclusion: the organizational AI conversation has matured from questioning value potential to confronting integration reality. Technical capabilities increasingly exceed organizational capacity to absorb them, creating an integration gap that determines competitive outcomes more than technological sophistication alone. Evidence and emerging practice point towards several actionable principles for leaders navigating this transformation. First, embrace experimentation as methodology, not exception. The absence of established integration models makes structured learning the only viable path forward. Organizations should establish formal experimentation systems with clear learning objectives, rapid iteration cycles, and mechanisms for knowledge capture and dissemination. Second, lead with transparency and explicit psychological contract renegotiation. AI integration disrupts fundamental assumptions about work, roles, and career paths. Leaders who acknowledge this disruption honestly, articulate new mutual obligations, and provide genuine transition support build the trust necessary for workforce collaboration rather than resistance. Third, redesign work intentionally. Technology capabilities don't automatically translate into effective work practices. Organizations must explicitly address task allocation, role definitions, skill requirements, governance frameworks, and process integration rather than assuming these elements will self-organize. Fourth, distribute integration leadership while maintaining coherent governance. AI's breadth and context specificity exceeds central planning capacity. Effective integration empowers local experimentation within clear guardrails, tapping distributed knowledge while managing enterprise risk. Fifth, invest in capability building as strategically as technology. Workforce skills, organizational change expertise, and continuous learning systems prove as essential to value realization as AI platforms. Organizations that systematically develop these intangible assets alongside technology infrastructure achieve superior outcomes. The integration challenge will intensify as AI capabilities continue advancing, generating ongoing work disruption rather than one time adjustment. Organizations building adaptive integration capacity through learning cultures, distributed leadership, strategic workforce investment, and structured experimentation position themselves to capture value from successive AI generations. For organizational leaders, the imperative is clear. The integration gap represents the defining challenge and opportunity of AI adoption. Competitive advantage increasingly derives from organizational change capability rather than technology access alone. The organizations that develop superior integration approaches and build the cultures and systems to sustain ongoing adaptation will define the next era of organizational performance.